Thanks. Online.
Enjoy your talk, having this.
All right, so welcome everyone back to our morning session, and I'm very happy to introduce Mike Jacobson, who will tell us about unconditional classical computation and applications.
All right, thank you very much. And so everyone else, I'd also like to sincerely thank the organizers for inviting me back to speak in this conference series again. As you can see, I am a veteran going way back. So I've been to all of these conferences, and very early on, this became one of my favorite conferences to attend. So I've got to now enough seniority in my department that I have some influence over what I teach and when. I used to do the teaching assignments, so I'd always arrange things that I was free teaching the fall semester, so I could come. It's just such an awesome conference to come. Class groups and applications have been since a bachelor's student. So being able to come and have a week-long conference or so with everything related to class groups and cool things with them is just so awesome. So great job, guys. Keep it up. It's an awesome thing to attend. So yeah, today, as mentioned, I'm going to talk about exactly unconditionally computing class groups and fundamental units of number fields. So thanks to Larry for setting this topic up. You've already seen, lots of really hardcore computations where, this becomes an issue, that you're looking at this really big and, can you do this unconditionally or not? And the answer is in a lot of cases, you really can't because it's sort of too slow. So my plan for today is I'm going to sort of show you just kind of the scope of the problem, how hard it is to do this in some sense. And then I'll talk a little bit about some applications, where we might care about having things unconditionally correct. And finally, I'll talk about sort of the two recent advances that we've been able to do in the area to try to improve the state of the art a little bit. So another nice advantage of coming to this conference to present is I don't have to spend a lot of time defining what a class group is. I think we've seen this a number of times already, and I think probably one thing I can assume everybody in the room already knows. So I'll fix some notation nevertheless here. So let K is going to denote a number field just of degree n, discriminant delta as usual, and O sub K is the ring of integers of the field. And so the class group, as we all know, I had to define it like persist to the end. It's the group of equivalence classes of invertible OK ideals. Order, it's a finite abelian group, as we all know. The class number is its order. And for a lot of things I want to do, I'm also interested in computing the canonical decomposition of the class group as a direct product of cyclic groups. And these MI is the order of the cyclic groups you get, or sometimes called elementary divisors of the group. So when I'm talking about computing class groups, that's what I mean. I want to actually get those things. So we also know the unit group of a number field is finitely generated of rank R. So when I say unit rank, I'm talking about this number of sort of the three copies of Z in this thing. Generators of each of those are called the fundamental units. And what I usually want to compute is typically the regulator. So which I'll define a little bit later. It's basically some volume of a lattice associated to these things. And in case you're wondering, typically if you know the regulator in a lot of cases, if you do need to get an explicit representation of the unit itself that you can compute with, that's usually enough information to cover that. So, and it's just easier to work with the regulator. Fundamental units get really, really, really big. So working with something that's like the log of them makes it a little bit more complicated. So I claim here that computing these things is a hard problem, conditionally or unconditionally, actually. Now, the first thing I want to do is show you kind of exactly what I mean by this. I've actually been called out on this statement a couple of times when I've talked about this sort of thing. And the reason is that, I don't know if some of you know, but I'm a computer scientist. That's where my primary training is. I've learned some math along the way, obviously, and my sort of research kind of straddles the border between disciplines. But as a computer scientist, I'm kind of living in this world of algorithms and computations and complexity and things like that. And when we talk about a problem being hard, we've got a very specific kind of notion of what that is in our heads. And sometimes I, forget that not everybody sort of has this shared perspective. So I think here, there are a lot of students and maybe some people, coming from a more pure math background who don't do computations for a living like I do. So I'm going to spend a couple slides here illustrating exactly what I mean by hard here, and by way of showing you the scope of this problem, and how difficult this unconditionally correct computations are. What I've been told,
In computation of regulator, do you have to compute the units, or are there ways to compute it more directly?
More directly. So yeah, the point is we avoid computing the units and manipulating them explicitly if at all possible, just because they're so large that you're doomed, if you want something efficiently in a lot of cases. Get the regulator first without touching the units. But then if we need the units, I can go get them afterwards. So when I've said this in the past, I've said, yeah, this is a hard problem. And I've had people tell me, well, what do you mean it's hard? And they would then proceed to exhibit nice little formulas like this. So look, you can just compute the class number with this thing, and what could be simpler, right? And there's lots of really cool identities for formulas for computing class numbers. This is, I suppose, one of the simplest I could find. It's just simply a series of these quadratic residuosity symbols. So delta over R here is the Kronecker symbol, right? The extension of Legendre's symbol. Right? And sure enough, so I implemented this query. It took me basically as long as it took me to type to implement it. It was almost correct. I confess I made a really dumb error. I blame jet lag, but for some reason I thought there was a plus sign in there instead of certain comments, and it wasn't working. But after about 10 or 15 minutes, I sorted it out, and I had a routine that was just happily, producing class numbers for me. Very simple, quick to implement, and quite lovely. So, so in some sense, computing a class number really isn't hard, right? This really easy formula that you can do, and it's easy enough that if you really wanted to, if you like working out Legendre symbols, reciprocity and things, it's kind of fun to do this and do examples of class numbers by hand pretty easily, right? And then that works great, as long as the discriminant, as I'll show you, is reasonably small in the field. This is perfectly fine and quite efficient. So the drawbacks of this, though, and there's where the computer sciencey stuff sort of starts coming in, is that this doesn't really help you sort of in terms, because of the computational hardness of the problem here. And the reality is that if you implement this formula, that it actually works terribly for large discriminants. So it just is way, way, way too slow. And even the other thing you might want to do here, so in a computational sense, I'm interested in computing class numbers for really larger and larger examples. Like Larry was talking about things like when the degree of the number field is getting really big, this becomes hard. It also gets hard if the discriminant starts getting big. And it also gets hard even if you want to do small discriminants, but you want a lot of them, right? So you want to do some sorts of tabulations. Then in any of those sort of circumstances, this formula just totally falls apart. So, and I'm going to show you that's how bad it gets, is to really illustrate the point here. And if you haven't done a lot of computations, I can tell you that, but until you sort of see it happening, it's really hard to understand what's happening. So what I'm going to show you here is just running times for computing the class group of imaginary quadratic fields of discriminant 2 to the k plus 3, the negative of that. Okay, so these are discriminants whose size, the number of bits and the integer representation of that is about k, right? So I'm going to increase k, and we'll watch what happens to the runtimes with these 3 different algorithms racing against each other, right? So the first one is the formula from the previous slide. This really nice simple identity that many of you probably seen and can do by hand. The second one is using what's called the baby step giant step algorithm that was invented by Daniel Shakes. At least one of us is known in person here. And and lots of great inventions in computational number theory. So that shows an improvement over the first formula. And the third one here, index calculus, is the state of the art. This is, from a computer science-y computational perspective, the best algorithm we've got today for solving this problem. It's the fastest. So let's see how this goes. So we'll start with discriminants of bit length 8. So I guess this is negative 271 or something like that. I don't want to do that. But what you see here is the times that I'm giving here are all in milliseconds, right? And Paris doesn't measure times in a finer granularity than that. And what it comes out to is that they all finish in less than 1 millisecond. So what this tells you is that if the examples you're working on are really small, it doesn't really matter what you're using, right? It's just going to be fast because the problems already seem small, but probably doable by hand. If I measured more precisely, there would be some differences apparent even at this size, but I don't know what they are. I would suspect that probably our simple formula at this stage might actually be the fastest one. They're sufficiently small. But let's make it a bit harder. We'll double the bit length of the discriminant. So I'm looking at about 2 to the 16 inside for the discriminant. So now, we're starting to see some problems with our formula here. Now, suddenly this is taking 10 milliseconds. Again, not very painful in practice, but compared to the other two, they're still less than a single millisecond. Like this one's now starting to, show some problems, right? And we keep going. Now we just double the bit length again to 32. And suddenly, this simple formula we've got is really starting to drag, right? I'm not sure that's milliseconds, so that's some number of minutes. I actually implemented a timeout when I was doing this, so I wouldn't let it go longer than 30 minutes on my laptop for a single thing. So it's less than 30 minutes at least. But compared to these other ones, you notice here, baby step, giant step is still less than a millisecond. But index calculus, kind of the one that I said is the best, is actually slower than baby step, giant step, which is another phenomenon in computational hardness, is that when we as computer science talk about this, we say that one algorithm is superior to the other. We're talking about this asymptotically, which means for sufficiently large inputs. So you see here already evidence that even though index calculus is the best asymptotic algorithm, at this point with these smaller discriminants, it is not the fastest algorithm in practice. Okay. So I can keep going, yeah. So now I get to k equals 48. So 48 to discriminants, and my simple formula is now taking longer than 30 minutes. And I just gave up. Maybe the giant step is still faster than the thing that I said is the best. So it's only taking about 3 milliseconds as opposed to 6. And keep going, go up to 64. But now things have switched, right? We sort of found the crossover. And I'm starting to see now the asymptotic superiority of the speed of index calculus coming into play. It's now at this size faster than baby step, giant step. And you can keep going, and now at 96 bits, baby step, giant step is really starting to grind to a halt. It's not quite at 30 minutes, which is pretty close. Whereas index calculus, it's about a second at that level, right? And 128 baby step, giant step, my laptop gave up. But index calculus, it's 22 seconds under a minute. So now that's an illustration when I say something is hard of the type of thing that I'm looking at. So it's got nothing to do with the simplicity of the algorithm, the formula. It has to do with how hard the problem is for a computer, especially as inputs start getting large. Okay. So I hope that sort of clears up and gives you an insight into sort of this sort of really important sort of aspect of computational or computations in general. Really.
This index calculus, that is the algorithm for computing the discrete logs, right? Is that the same one or?
Same type.
Same type.
So I don't know if you all heard online, the question is index calculus for the same algorithm for computing discrete logarithms? And it's the same general family. So things like the number field sieve for factored integers is an index calculus algorithm, as a number field sieve for discrete logs. And same type of thing here where you're doing basically collecting relations and doing linear algebra. So, so yeah, same family.
Yeah, Mike?
Yeah.
How do you guarantee your answers are right on the last two columns? I mean, the first one, you're right, if it works.
Yeah. That's a very good question. And in fact, you might notice at the top here that I've got a little asterisk beside and you might have seen, when you talk about like sports records, sometimes, someone's done a remarkable achievement. You might see an asterisk beside your name, there's something kind of fishy about it, right? I like baseball, and Barry Bonds is sort of the all-time home run hitter. But when he was getting his records, he was full of steroids. So like, the record, they recognize that he's the one who no one's hit more than him. But there's this little caveat that well, it's not fair. And so yeah, that's exactly what I've got indicated here. So the star is that both of those algorithms, their correctness requires assuming the generalized Riemann hypothesis. So I don't know, a priori whether those are truly correct. I mean, in my heart, I do know because I believe the generalized Riemann hypothesis is true, and I don't really doubt it. But I can't prove it. That assumption. So this is another phenomenon, again, a lot of computational number theory, that a lot of times you can make this trade-off of rigor for speed by assuming conjectures like this. And algebraic number theory, assuming the generalized Riemann hypothesis, often buys you a lot. So what we need then is some way to certify that when I get these class groups that they really are correct unconditionally. Remove this assumption to GRH. Now, I was using Pre's implementation of these things, and it also provides a function to do just that. So there is a verification. I can take the output from a Pre's implementation of the index calculus algorithm, and I can ask it to give me a rigorous proof that, that the thing really is unconditionally correct. So let's see how that performs now, sort of what ballpark we're in for the times for that. Well, if I start at the small example, 271 or whatever it was, still I'm under a millisecond. So that's looking good, right? Verification sure doesn't seem so bad. It's really not much worse than computing the thing to start with. But if we keep going, oh no, already going to 16 bits, we're already at a millisecond, where every, computing the thing was less than a millisecond. So now, I'm probably starting to worry a little bit, right? That this isn't going to end well. Okay. So sure enough, going to 32 now, yeah, verification's blowing up a little bit. It's close to a second. Notice it's not as bad as using my simple formula. It doesn't blow up as bad, but it's starting to grow a lot more than just computing the things itself. So already, if I get to a 48-bit discriminant, so I'm looking at 505 seconds, so getting close to 10 minutes already just to do this verification. And I get to 64 bits, and Pre can't do it in under half an hour. And if any of you have tried this, I mean, even like moderately sized sort of things, Pre often just gives up, right? You have to certify it. And so that's pretty bad. So the moral of this is that, if I really want unconditionally correct results, it's hard, right? Much harder than just computing the thing under the GRH. So here's a little summary of the state of the art of the problem. So the slide looks gross, but I'll walk you through it a little bit. So what's at the top here is the kind of the standard sort of function that represents the running time of index calculus algorithms. So we call this sort of a sub-exponential complexity statement. So the function is basically e to some constant times the square root of log delta times log delta. So it's kind of the order of a e to the square root of log delta, right? And so that's something, it's not quite exponential, right? Like e to the delta would be an exponential function of log delta. This is kind of less than that. And sort of these sub-exponential things kind of lie between like polynomial functions and exponential functions. And that's what index calculus gives us. So again, that's sort of the state of the art. So if I'm okay with the GRH dependent outputs, then for a number of fields of degree of bigger than 2, I'm getting the sub-exponential complexity. And the notation here, this is again computer science lingo here. We use this so-called big O notation to represent essentially an asymptotic upper bound here on essentially the number of computational steps required to solve the problem, right? So that's all it is. I guess in math, what's the notation, like greater than or something like that for some asymptotic statement. That's all that means, just in our language. So for a quadratic field, you can do a little bit better in terms of that constant beta. So it's a little bit simpler than the general case, but sub-exponential if you assume GRH. But if you want it to be unconditional, and here's where you see when things get bad. the number of steps that you require to verify the class group is of the order of the square root of the discriminant, right? So that's now exponential in basically the size of the discriminant. And that's why on the previous slide, you see the time required for blown up a lot faster than the other two algorithms. Incidentally, the cute little formula that we use, why does that blow up so bad? Well, the number of steps there, if you remember, it's a sum of these Kronecker symbols for all r from 1 to the discriminant. So the upper bound of the complexity of that is we go delta to the 1 instead of 1/2. And that's why that one, just blew up so fast compared to everything else. Okay, so for verifying the class group of a quadratic field, it's still square root of the discriminant. In fact, I don't know of any way to do faster than square root of discriminant if you want to certify the class group. Unconditionally correct, or the class number. That you seem to be very much stuck there. If all you want to get is the regulator, though, you can do a little bit better. So Johannes Buchmann in the late 80s showed that you can compute the regulator unconditionally using a generalization of Shank's baby step giant step method and basically times square root of the expected size of the regulator. Right? So the regulator is, well, the regulator times the class number is of size squared of delta if we believe that class numbers are small most of the time, or 1 infinitely often, for example. Well, at least nothing else, a good upper bound on the regulator is the square root of the discriminant. So delta to the 1/4 is the square root of that you get from baby step giants. Now, in the quadratic case, we were able to do even better. We were able to knock that down to delta to the 1/6. So what I'm going to talk about for the rest of the talk here is, first of all, a little bit about just more motivation, where you might care about getting this done unconditionally. In fact, we had a preliminary version of this paper that we submitted to ANSI. It got rejected, and one of the comments was, "Oh, it's a cool algorithm, but it'd be nice if there were applications." And they're sort of it's all that. They're can empathize with this. We've never tried to publish stuff, but yeah. So I will, just in case the referees here, I'm going to tell you why I care. And then also, again, 2 little results that we've had to improve the state of the art. So I'll say a little bit about how we get 1/6 and how we were able, in fact, this paper that got rejected, we were able to improve the general case to delta 1/6 as well.
What is this verification actually? So what does verification means? So
yeah, so that means that you run a computation and it tells you whether or not the output that you have in either the class group or the regulator, or both in some cases, whether or not it's rigorously correct without needing to assume GRH. And so the typical thing is that you run, again, index calculus is the fastest algorithm. You run it, it gives you something that it says is the class group and regulator, but it can only tell you that that is true if you assume the Riemann hypothesis. Verification is the additional computation and certified using unconditional class group and the regulator.
But doesn't unconditional also mean you're not assuming Riemann hypothesis?
That's what I mean. When I say unconditional, that means that I don't need to assume any Riemann hypotheses. The difference between the verification process and what?
And the unconditional results?
Well, that's what it is. So, yeah, so I'm just saying that the algorithm here, there's a special verification algorithm that Curry implements. But these 2 other ones, so if I only want to do the regulator, I'm not going to do index calculus and this post verification. I'm instead just going to run the baby step giant step algorithm from scratch and compute the thing unconditional. That's what that means. Yeah, sorry about that. You had a question?
This 0-3 regions play a role for the unconditional result.
Which
0-3 regions play a role. Do you use the 0-3 regions? You don't.
well, 0-3 regions? No.
No, you don't need to. Okay.
No, it's there's actually, so I had a slide about this earlier today. For time, but
we can talk later on.
yeah, well, it's pretty simple actually. So there's 2 places where you need your GRH. One of them is there's a bound on the norm of prime ideals you need to generate the whole class group. So if you assume the Riemann hypothesis, then that bound is a constant times log delta squared. So it's pretty small. If you don't assume GRH, you need to take to have a generating system of the class group, you need to take prime ideals of norms bounded by square root delta by Minkowski. And so that's a crucial one, right? If you want to certify it, and that's where the square root of delta complexity comes in, is because you need to, what you get is a class group, you get actually a subgroup generated by some finite set of prime ideals that you've used for the computation. And typically you can't use everything that you need to guarantee rigorously that you have a generating system. So the verification, a large part of it, is certifying that all the other prime ideals that norms up to the Minkowski bound are contained in the group that generated. And the other place you need it is you need it for sharp estimates of the error of approximations to the L1 chi function, or the for the general case for I guess the negative zeta function, because you use that along with the analytic class number.
You can use the zero-free region and can get little better. Maybe
Possibly, yeah.
that place at least you can.
Yeah.
First case also, I think there is a possibility of using, maybe, I'm not sure for the first, but the second one, I'm sure you can use zero-free regions.
Yeah, it's possible. I think what I know for the state of the art though is if you assume the GRH, you can get a sufficiently accurate approximation really, really quickly. And everything else I've seen to get an accurate enough approximation requires in your truncated product a big O of root delta terms. So I don't know if zero-free regions can get you below square root of delta, that'd be really cool. And even if it just makes
Maybe that doesn't mean, because I have no idea about computation.
that's the two places you need. So
Like, do you have any problems with not knowing whether an ideal is whether it's principal or not?
well, so what
Do you need GRH for that?
well, again, what you need is that you have to start with a set of prime ideals that you know generate the class group, right? The whole thing. And if you assume the GRH, you get some finite set of relatively small norms. And verification means that all the prime ideals up to the Minkowski bound that you didn't use, you have to prove that the equivalence classes they generate are contained in the subgroup you started. So it's not principality so much. It's just that here's an equivalence class generated by some bigger prime ideal, a bigger norm. I have to show that I can write that as some linear combination of elements in the class group. So it's an equivalence test you have to do, which are also hard to do. So yeah, so that's kind of the state of the art. So now again, well, why do we care about unconditional things? Well, my favorite application from when I was a young bachelor student was generating numerical evidence in support of things that we can't prove. Okay? And we've seen already in the last couple of days various examples of this. Cohen and Leinster's heuristics have come up, and the reality is that we can't prove a lot of arithmetic properties about even class numbers. So simple things like what's the probability that some prime number divides the class number? We don't know, but Cohen and Leinster give a really convincing heuristic estimate of what the probabilities should be. And pretty much all the time, people, when you do calculations and you try to just tabulate as many class numbers as you can, and you look at, well, what's the observed, proportion of those things that are divisible by p, they pretty much match what Cohen and Leinster predict. There have been some bumps along the way. So in some settings that people have forgot to account for certificates of unity in some fields and such, but they keep we figured those out, they get adjusted, sort of pretty happy with it, but no one can prove that. So the best, so getting numerical evidence is important. There's other things like tight bounds on L functions. Due to Littlewood had some estimates. I did work earlier in my career of do these tabulations in order to provide some evidence that those bounds are actually true, that there weren't any exceptions. But this question of how many prime ideals are required to generate the class group itself, we use that in a fundamental way in the algorithm. But it's also of interest to generate evidence to see if those bounds are correct, or whether, or even better, what the real bound is. Is constant times log square delta correct, or is it even smaller? And in fact, in practice, usually you can get by a much smaller factor. Well, prime ideals to do this. So it's interesting to know that. Larry talked a little bit about various heuristics related to p-group extensions of the quadratic fields, and lots of cool things going on with that. And all these sorts of things, no proofs are in sight. So you'd really like to get numerical evidence to support them, and it'd be even better if the results were unconditional, right? Now, and you can't always do it. We've seen why, even in the quadratic case, verification is hard. And I think the examples Larry is trying to use probably hopeless, and you might be stuck with GRH, right? But things like testing Littlewood box results, right? So these are consequences of the GRH itself. And so if I'm generating numerical evidence in support of that, and the correctness of my data is conditional to GRH, I mean, that makes you feel a little bit queasy, right? So you really like to have things unconditional or stuff like that. And one other really nifty application is sometimes solving Diophantine equations that requires this too. So there's numerous cases where you have some funky Diophantine equation you want to solve, and you can end up reducing the problem to solutions of, say, Pell's equation, which in turns we know reduce to finding fundamental units of, say, real quadratic fields. One example that I played around with some years ago was an equation by Schaefer, where he's looking at whether or not it's possible to represent a consecutive kth powers of integers of this k as a power. Right? So Akos Pinter and Gary Walsh approached me with this problem. They had found a nice way for the case q equal to 2. So looking at sum of kth powers being squares, they could reduce this to finding points on elliptic curves, and then in turn reduce that to looking for units of certain quadratic fields that have particular properties. So at that time I knew how to compute units and then do work with them. So we were able to resolve this equation for even values of k up to 70. Now the thing is, though, what we had to do is you take a particular value of k. This gives you a bunch of discriminants of different fields, and I had to compute their fundamental units. And then from there, look at particular powers and see whether they have the properties that were required to give rise to a solution to the equation. Right? Now, the thing is, I mean, if the unit you start with isn't fundamental, you start powering it up, I'm possibly missing things, right? So it's really important that I start with the actual generator, the unit group. And as you see here, for k up to 58, we were able to resolve this unconditionally, and it's precisely because up to that point, the discriminants were still small enough that I could do this verification unconditionally. Whereas to get up to 70, I couldn't. And I was stuck having those results being conditional with GRH. So another place for this.
How big do the X and Y turn out to be in these solutions?
Oh, so the answer is there are 10. Yeah, there's actually one. I think there's a trivial solution, and there's I forget what it is. It's something like 24 and 70. There's like one kind of sporadic solution, but after that, there's.
And so when k is odd, are there?
Oh, I don't remember what the situation is for k odd. I think k even, we could do the game with the elliptic curves. It's a different ballgame. Okay. So the rest of my time, I'll advertise a little bit about some of the stuff that we've been able to do to help with unconditional computation of these things. So the situation here, the first one we'll talk about is verification fundamentality of units. So what we have there then is we're given some set of independent units that generate a rank R, the sort of subgroup of the unit group. So it's full rank. I just don't know whether they're fundamental or not. This point. And this is exactly the situation where if you run the algorithm in Paris or Sage or something, and it says, hey, here's your fundamental units, right? That's essentially the situation I've got. It typically gives you something that's full rank, but it can only tell you that they're fundamental under GRH. So what do I do? Well, the first thing, I actually don't want to work with the units themselves again, because they're big. They're of size basically an e to the root d. So when discriminants are large, these things are enormous. You can't really take them down and manipulate them. So we work in the image of the unit group under this sort of a logarithm. So we're basically just taking an element of the field, and we're represented that as a vector of logarithms of the different embeddings of the number. So in sort of the standard way that in fact you use to define the regulator. So if you look at that to the log map, then you apply that to the unit group, and you get a sublattice of the real numbers to dimension R, and the determinant of the fundamental domain of that lattice is what the regulator is defined to be, roughly speaking. And a basis for that is you apply the log map to your fundamental units. get that. So what we have though from our input is I've got these units epsilon1 prime and epsilon r prime. I don't know whether they're fundamental. What I do know is that if I look at those under the log map, they generate a sublattice of this whole thing of finite index. So my problem then, if I want to certify that the things that I have really are fundamental, is to check and verify whether the index is I. Now again, there's one. The index is defined as I as the notation we use. I want to see that it's one. So the situation again, if I get those units from the index calculus algorithm, if I believe GRH, I know that the index is one, right? GRH, they're correct under GRH, and this is the process of just doing some computation to rigorously guarantee that it truly is one. Okay? So there's two ways that I know how to do this. And one is Bookman's method, step, giant step. And what that is essentially is a way to sort of search a region of some sort of bounded volume in times square root of the volume. So if you want to search some region, you can do lattice enumeration, right? To just sort of find all the vectors of the volume search. You do a combination of enumerating just a small part of it and using ideal arithmetic to kind of jump around in the rest of the region in a clever way. Bookman showed that you can reduce the complexity, cover the whole region in times square root of the volume. And that's where you get the delta to the 1/4. Now, the problem with that, though, is that I mentioned the dirty words lattice enumeration as part of this. And that is a nasty thing to do when the dimensions of the lattice start getting big. So even though as a function of the discriminant, as the discriminant is growing, you know, the number of steps I need to do this giant step is of the order of the 4th root of the discriminant. The dependence on the degree of the number field, and in particular the unit rank, is bad. It's exponential. So this sort of thing you would only expect to work for sort of small degree, small unit rank sort of cases. And in fact, for quadratic fields, unit rank 1, this works great. Use babysit all the time. For complex cubic fields, they've done it, but that's going to limit you if you get to like degree. I think Larry said 53. I think this might not be what you want to do. So the other approach, and this is actually a component of what's implemented in things like Paris, is that you try to just eliminate index divisors. So you try to find a lower bound on the regulator, and then that gives you, in conjunction with the determinant of the lattice that your units generate, that gives you basically a range of possible divisors, of prime divisors of the index. And you just simply run through each one of them and try to certify that to no pth roots of any of the units that you have are good self-units. Okay? If they are, because that's what the index means. That means that there's some pth root of the unit that is itself a unit. If you can certify for every possible prime divisor and none of them satisfy that, then you're done. You're guaranteed that the index really is one. So the problem with this is that you know, if you could get a really big lower bound on the regulator, that reduces the number of primes that you have to check. But just a priori, if I hand you a field and say, well, what's lower bound on the regulator? Poston's Assenhouse and further future collaborators that they work with later have clever ways to do that, but still the bounds are really small. They're like in the order of log delta all the time. Which means that the number of primes that you have to check, given that you expect the volume of the thing you have to search to be square root of the discriminant, the number of things is going to be, well, the number of primes up to that size, which again is going logs from the prime number theorem and such is more or less square root of the discriminant. Okay, so that's pretty bad. Asymptotically, as the discriminant grows, this is worse than babysit giant step. But a big reason why people like to do this and things like Korean stuff is that there's no lattice enumeration. So the dependence on the unit rank sort of gone. So that's why you find them.
But how are you checking that pth roots of units, whether you yield new units without doing an exhaustive with lattice?
Well, that's where Poston's Assenhouse and some later collaborators found really nice systematic ways to do that. You can basically, for every prime, you have to do basically just R pth root test, basically one for each one of your units that you have. And they have a clever way of sort of constructing things that you want to do. And then the pth root test is basically you move to the log lattice, and you get a vector, the log vector of a particular unit, and you just divide the coefficient by p, and you sort of look at the magnitude of log vector of the unit.
But how do you know like the product of epsilon1, epsilon2 is not a peak power?
Yeah, that's, so there's two ways you could do it, I think. You can take, one way to do it is you have to take basically E to the R different sort of linear combinations. That's why all of them. But yeah, it's a little complicated to explain. They have a way to get that down to just R tests. So it's pretty effective. And there's other cool things that they do as well. So like they can, for example, in most cases, if P is not an index divisor, they can certify that quite quickly with linear algebra mod P. And sometimes it fails and you got to work. Although the complexity is square root of delta and that's what limits it, the individual tests are actually pretty quick. So in a lot of cases, this works okay.
Could you speak a little bit more to how we do lattice elimination?
Think of post. The standard algorithm that people use to do that. And yeah, that's what it is. It's just exponential complexity of the dimension of the lattice. So it's hard.
Okay.
In the sense that I meant earlier. All right. Now, our improvement and the way we got that down to L316 is to do basically a clever combination of those two things. And the thing is that, I mean, if you think about what Curie is doing, just looking at every possible divisor of the index, basically determined by the volume of the lattice you're certifying here. Well, if you can get a bigger lower bound in the regulator and certify that the regulator is not less than that, you reduce the number of primes you have to check. Okay? Now, the formulas that we have for generating these lower bounds don't give you much. But what you can do, though, is you can use this baby step, giant step search strategy. You can say, well, I want to check a volume of whatever size I want. And I can use baby step, giant step to verify that there are no units in that volume in times square root of that volume. And so I pick a bound B basically, and I say, well, I'm going to look at this region of volume determinant lambda prime B. Then if I can verify there's no units in that volume, then all I have to check is prime possible index divisors up to B. And by optimizing the choice of B to minimize the total time of all of that, you get that the complexity is determinant of delta prime, the volume of the region that I was given, to the power of 1/3 instead of 1/2. So that's, again, very simple idea. And that's exactly what and me and Hugh Williams did in 2007. That's what I used in this computation of the Schaefer equation to certify the fundamental units I was doing. And Randy E, one of my PhD students, and Patran as a co-supervisor, were recently able to do this, for, again, number fields of arbitrary unit vectors as well, with the same complexity. And again, the delta 16 comes from if you assume that under the GRH, for example, that the index really is 1, then the determinant of lambda prime is of the order delta 1/2, and that's the power of 1/3. Which, if you remember my tables of racing things of different powers of delta, knocking that exponent down makes a big difference. Exponential time, and again, these search things are completely unconditional in terms of their correctness. This is a rigorous certification that you do have fundamental units. The complexity, however, I want to say that this is the complexity. I need the GRH for the assumption that I true is. Then I get it. So that's one thing we were able to do. And very quickly, I'll just mention. So the other thing, I should show preliminary results first. So we're still working on this. We're working on just doing better empirical optimizations, benchmarking. But here's just a couple examples of unit rank 1, 2, and 3. Discriminants are roughly size 60 bits. The regulators are half that, 30 bits. And you can see Curie can't certify the fundamental units in up to 12 hours on a desktop machine. Baby step, giant step works a little bit better. These are runtimes in minutes. But by doing this clever optimal combination of the two strategies, it becomes a lot faster and makes things that were previously out of reach a bit more reachable. And so now the other thing was the tabulation of class groups. So certifying an individual class group, I don't know what to do better than square root of the delta complexity. But the problem of trying to compute a whole bunch of class groups, say for fields of bounded discriminant, there we can do some really neat things. Get some nice groups, even in the unconditional sense. So here's a couple examples for what's been done for imaginary quadratic fields. So Gauss, of course, started the whole game here. This is a much abbreviated history, but Duncan Buell did a major advance in this last year's. Former master's student, Founder Hugh Williams, extended the table quite a bit using some nice tricks. And what I'm going to talk about, though, is this work with Anton Mosinov and a recent extension of that we've done recently. So if you want to do this unconditionally, what can you do? Well, you can either use one of these faster conditional algorithms, compute your table, and then try to find some way to go afterwards and check that everything is correct, like I've been talking about. The other approach, and what Anton and I did, is you could try to use some way to just generate all of your class numbers in one shot unconditionally. And you've seen this probably happening if you think about how do you find prime numbers, right? If you want to find a single prime number, you could try trial dividing it. And if you wanted all the prime numbers to abound, you could do that for each of them. Or you could do the Sievert-Vericosteny. So do this nice procedure on the entire range at once and get the whole list of primes way quicker. That's the philosophy we're trying to do here. Is there some kind of batch computation like that works? And there is, and this is what Ben Kane was talking about yesterday. So the simple approach is we're looking at generating functions for representation numbers of integers as, in the simplest case, sums of 3 squares. As Ben showed us yesterday, if you can compute that number, R3 of n, then there are simple relations to the class group, the class number of the imaginary quadratic field discriminant minus n, right? Except for the case when n is 7 mod 8, then the representation number is 0 and we're out of luck. But for the other 3 congruence classes of the discriminants mod 8, we can do this. And the cool thing is that this generating function with a really simple expression has the cube of this simple series. So the algorithm then is I compute this series of theta of q. It's, I represent this as some polynomial. Basically, I truncate the degree of this infinite series, and I cube it using fast polynomial, fast Fourier transforms, all the fancy tricks, and that gives me, a polynomial where I just read off the representation numbers and compute the class numbers, and that's unconditionally correct. I don't need any Riemann hypothesis for it. Reduce the problem to polynomial arithmetic, and I get my whole table one shot. Okay? Now again, the case of discriminants that are 1 mod 8, because I can't represent integers that are 7 mod 8 as sums of 3 squares, I got to do something else. I fall back to the other method of computing verified after the fact. But in the whole, I get three quarters of my discriminants I get kind of almost for free, and this works beautifully. So to compute the tabulation up to discriminants of 2 to the 40, so just 4 days of the parallel computation. But the 1/4 of the tough cases took about 2 days on 1,000, so it's way longer. So that series worked really great. Now, the recent work that we've done with a soon-to-be master's student, Anthony Vasquez and Anton again, is and this is actually something that came out of an earlier edition of this conference. I had talked about that work at the HRI previously, and Ben Kane said to me, well, hey, there's nothing special about this ternary form x1 squared plus x2 squared plus x3. If you try things like this one here, x1 squared plus 3x squared plus 3x3, the representation numbers of those, as we saw yesterday, are also related to class groups of quadratic fields. And in particular, if I compute those representation numbers, I can get some of the congruence classes of discriminants I was missing. In particular, if I mod 24, I get to 7 mod 24, which are some of the 7 mod 8 ones. I can get 15 mod 24, but I can't get 23, right? But that helps already. I can now do this series to get 2/3 of the missing classes. And Ben also told us, well, if you look at mod 120, there's another ternary form that will get some more of those classes. I can get everything that's 23 mod 120, 47, 95. I'm only now missing the one congruence class 119 mod 120. So I can do this. I'm never going to get everything, right? But I'm going to get always with larger and larger moduli, different forms. I can get more and more and more of these missing cases. And at some point, there'll be a balance, right? I'm doing all this extra work with series arithmetic, but, that our ongoing work is to figure out where that's going to be. What we've shown so far is just using the formulas mod 24 already gives a pretty substantial improvement. So I was hoping Ben was going to be here to show that this idea actually works, but I'll have to tell him myself. But hey, thanks, Ben. It actually works. So to finish up, so again, tabulation, we can do some good things, at least in the imaginary quadratic case. Fundamental units, we can do a bit better. What about tabulating real quadratic fields? Well, we've got a good idea there too. I don't know how to do some trick like with these theta series. I have no idea. Catherine Brinkman seems to think that there's a way to do it. I don't see it yet, but it might be possible. But what we can do at least is just compute the class numbers and regulate master asymptotic algorithm and do a verification afterwards. And this is a project that I'm working on with Andrew Booker and one of his students, Andre Powell. And the idea there is that if you have a table of these class numbers of real quadratic fields, you can use the trace formula of these automorphic forms, Moss forms. And what you get is an identity, which on one side is a function of your class numbers and regulators, and on the other side is a function of your Moss forms up to some particular eigenvalue. And so you simply just compute both sides of that. Okay. And that's, again, that's an unconditional thing. There's no GRH needed for that. And this actually works. So we've implemented all this. We're just waiting for my student, Austin Doherty, to finish tabulating the class numbers, and we'll run the verification and write this up. And hopefully by the end of the year, we'll be able to have a big extension for real quadratic fields. And finally, you might ask, well, you know, I'm limping along, going from imaginary quadratic to real to complex cubics to be the next simplest ones, perhaps. Nice unit rank one thing. And I'm really hoping this idea will work. So Ken Nakamura in the 80s had a series of papers of computing class numbers and fundamental units using what's called the elliptic unit. And this is something that you get from the theory of complex multiplication. What happens is you can compute basically the fundamental unit of complex cubic fields, the power of the class number, via evaluation of the Dedekind eta functions, taken over representatives of certain ideal classes of an associated imaginary quadratic field. So this is really cool. And why I think this is going to work really well in our case is because, well, to compute the eta functions, I need to have class groups of imaginary quadratic fields. But with my work with Anton, we've got a massive table of those. So I don't have to compute those class groups. They're given. I just read them out of a table, right? So working out the eta function should be really easy, and I can get these elliptic units. But now the next thing I need to be able to do is, given, well, a power of the fundamental unit, I have to figure out what the fundamental unit is. But that's exactly the work that Randy and Hotran and I are now done that I talked about earlier. So we think we've got the pieces together to really make this work quite effectively. And if this really does work, Ken has other papers for certain quartic fields, I think sextics, and I guess I can have tabulation projects to keep talking about for numerous conferences to come. So that's a little glimpse into some, you know, humble progress we've been able to do in this unconditional computation game. I'll stop with that. Thank you all for your attention.
Thank you very much for the nice talk. And we are running a little over time, so let's maybe move on